So thanks, Alex, for that introduction, and thank you guys for coming today. I'm excited to be talking to you because I was in your shoes 5 years ago. I was an intern here in 2010, and so I'm excited to be sharing with you some of the things that I have learned about and been working on since coming to grad school. So in particular, I'm going to be talking about the study of galaxy formation and using a tool called a cosmological simulation for that purpose. So I'll be talking about, in general, why studying galaxy formation is hard, why cosmological simulations are useful, what we do here at the CfA, and what I in particular have been working on for the past year or so. So I'm sure most of you have seen these beautiful Hubble images of galaxies in the nearby universe. This is a nice grand design spiral type galaxy, flat, star forming, and you have probably been told in your undergraduate courses that there are 3 basic types of galaxies. Spirals like this, elliptical galaxies, which are less exciting to look at and are no longer forming stars quite as rapidly, and the quote-unquote irregular galaxies that are just kind of blobby looking and don't really fall into any particular category. And these 3 morphologies are good general descriptions of the type of galaxies that we see, but they don't even come close to describing the diversity of shapes and sizes and colors that galaxies really have in the local universe. So there are some galaxies that have friends. There are some galaxies that have close friends. There are some galaxies that are having a bad day. There are galaxies that barely count. There are merging galaxies. There are barred galaxies. There are hungry galaxies. There are bored galaxies. There are dusty and warped galaxies. There are egg-shaped galaxies. There are tidally disrupted galaxies. There are jet galaxies. And all of this is just in the local universe. This is close enough that we can get really nice high-resolution HST images of these galaxies. And when you go further back in time, you pick up even more different kinds of galaxies, like high-redshift clumpy spiral galaxies and red compact elliptical galaxies. So the challenge of studying galaxy formation is to try to explain how you get all these different types of galaxies, and not only to give some way in which you could form each of these types, but also explain why we see them in the kind of distributions that we do. And as you might imagine, this is a very challenging problem because galaxy formation is very complicated. But there's an additional challenge to studying galaxy formation, which is really fundamental, and which is that you cannot watch it happen. Galaxies form and evolve on timescales of millions to billions of years. So if you're just sitting around waiting for something to happen, you're going to be waiting an awful long time. So it's not like something like supernovae where you can watch it evolve. So to get around this, the way that observers study galaxy formation is to get snapshots of galaxy populations at different redshifts and try to make connecting lines between them. I'm sure you're familiar with the concept that if you're an observer over here, the further you look away, the greater distance you're looking away, or redshift, the further you're looking back in time. So something closer to you is from essentially the same age of the universe as you are. Whereas when you go further and further back in time, the light has been traveling to you for longer and longer, and therefore it was emitted when the galaxy and the universe itself was younger. So looking further away looks backwards in time. So, for example, if we were to look very nearby at a redshift of 0.003, you see the Virgo cluster. Now, these galaxies are from essentially the same age of the universe as the Milky Way. They're what we would call the local universe. If you look further away into the good south field, you can see galaxies of up to a redshift of 3.5 or so, which is 10 billion years ago. And if you look even deeper, say into the Hubble Ultra Deep Field, you can get galaxies of up to a redshift of 6. So we're starting to really push back into the very, very early times when the universe was very young. And so when we're studying galaxy formation, essentially what we're trying to do is identify some galaxies here in the deep field, which are from a very long time ago, and try to identify their possible descendants in something like the good south field and eventually in the Virgo cluster. So if you'll permit me to make an analogy here, it's kind of like trying to study human childhood development by looking at a series of photos of kids at different ages. So if we are going to use my life as an example here, low redshift, the Virgo cluster, would be something like the astronomy department picnic from last fall. I look pretty much the same today as I did then. I'm the one wearing the sunglasses in the shade. And if we were to go to a little bit higher redshift, it would be something like this. You might recognize one or two of the people in this picture. This picture was taken almost exactly 5 years ago. You may be able to guess what we were doing this day. This was the day that we went to Chinatown for dim sum. And these are all the students that were in the RU with me, and Jonathan, of course. And I'm the one squinting because I don't have sunglasses that day. Now, if I go to higher redshift, let's say 15, 16 years ago, it's something like my 4th grade picture, class picture. So this is Larchmont School, Mount Laurel, New Jersey. And given these two pictures, you can probably see which one is me, right? I'm the one with the awesome fashion sense in the middle. And so if I were to give you a selection of pictures at different stages of my life, when I'm different ages, you would be able probably to pick me out of all the pictures and put together some timeline of my growth and development. So local universe, let's say redshift 2 is middle school, 4 is elementary school, high redshift is early childhood. And so this is not quite the right analogy yet to us trying to figure out galaxy formation. And in order to make it a better analogy, I'm going to have to introduce you to a couple more people. So this is a picture from when I was much younger, obviously. This is me. And these 3 girls are my little sisters, Megan, Lauren, and Madeline. Now, if we go to the present day, we're pretty similar. We all enjoy chocolate souffles and hot tubs and reading in hot tubs and aquariums, although some of us more than others, and gingerbread houses. And I've snuck in a cousin here just to throw you off. Now, the 4 of us all have pretty similar initial conditions, by which I mean genetics, and we all developed in a similar environment. So it's a good approximation to say that we all have a very similar developmental path. If you look at me as a 4th grader, it's probably pretty similar to what Megan was like as a 4th grader, and so on and so forth. Anyone with siblings will tell you that this is not a perfect approximation, because you can grow very differently and become very different people, but on average, you are going to be more similar to your siblings than you will be to a random person selected from the population. So when we're studying galaxy formation, it's not like getting pictures of me at different stages in my life. It's more like having my 4th grade picture, Madeline's 2nd grade picture, Lauren's 8th grade picture, and Megan's kindergarten picture. And now your task of identifying potential progenitors and descendants gets a little trickier. So this is me here. If you selected on straight hair and glasses, you might be able to find my sister Lauren at redshift 1. My sister Madeline is here at redshift 4. And if you decided to use overalls to connect people between different redshifts, you would identify my sister Megan at redshift 6. And so this kind of evolution is the best that you can hope for to identify galaxies which evolve in similar ways and try to link them together across redshifts. So the point that I'm trying to make, which I hope you have picked up on by now, is that connecting galaxies at different redshifts is very challenging observationally, and there's a lot of uncertainty associated with it. We haven't quite figured out how to do it really correctly yet. But there is a way that you can actually watch galaxies evolve, quote unquote. And let me show you one example. So this is the simulation done by Volker Springel of 2 disk galaxies undergoing a merger. Each of the points of light here is a star, and the color of the light indicates the age of the star, with younger stars being blue and older stars being red, just like in real life. So these galaxies have completed their first pass and are starting to come back around. And you can see the development of the kind of tidal features that we saw, for example, at the beginning when I showed you the pictures of some actual galaxies. Got a nice tidal tail right there. So they're coming around now for their second pass, and after that, it's going to be not very long before they coalesce entirely. And so now, if we look at this galaxy, if we pick it up at this point in time, we would probably call this elliptical, right? So this kind of simulation has showed us that one way to produce an elliptical galaxy is to merge together two spiral galaxies. So we have a plausible link between these different galaxy types. And this has been a very valuable tool. But there are a couple of questions that pop up almost immediately when you think about this kind of simulation. First of all, how common are the kind of initial conditions that you assumed in that simulation? We've shown that, yes, you can merge two disk galaxies to get an elliptical, but how often does that actually happen in the real universe? How important is that mechanism? And also, of course, in any simulation, you have to assume a set of physical models that govern the evolution of the simulation. And there's questions about how robust are those models? And that's a very good question. But to address this first question here, how common are those initial conditions? What we really want to do is to get a set of so-called cosmological initial conditions that allow you to simulate populations of galaxies at once rather than just one or two, so that then you can make statistical comparisons to observations. Now, this kind of approach has been done extremely successfully with dark matter-only simulations, where you take an enormous volume and form dark matter structure within that simulation. As the name suggests, the only thing in the simulation is dark matter. But it shows you something about the structure of the universe on which galaxies are evolving. So the way that this works is that you take something like the CMB that tells you about the structure of the very early universe, the statistical properties of overdensities and underdensities at those very high redshifts, and you create a set of initial conditions that have more or less the same statistical properties. So this is a density map of dark matter at redshift 18.3 in the Millennium simulation. And then you take these initial conditions and evolve them forward using gravity and cosmology. So if we go to redshift 5.7, you see the coalescence of those overdensities and the expansion of the underdensities. Going to redshift 1.4, it's even more extreme. You start to see the formation of these filaments, the so-called cosmic web. And to redshift 0, you see a massive cluster and a massive void. So now we're flying through the three-dimensional space in the Millennium simulation at redshift 0. So this is its final state at the present day. This is all dark matter structure here. So within each of these dark matter overdensities, you would expect there to also be a baryonic overdensity, and that is where you think that galaxies are going to form. And you see these long filaments and big voids spanning the universe. And this is the skeleton, the backbone upon which baryonic structure will also form. So this kind of major dark matter overdensity is probably going to correspond pretty well to a major galaxy cluster with lots and lots of galaxies in the same place. So this type of approach, even though it's only dark matter, has been extremely valuable in telling us something about what we might expect about the clustering properties of galaxies, for example, and the mass distribution. But of course, what we would really like to be able to do is to simulate the baryonic processes on top of and coincidental with the dark matter structure. And as you might be able to imagine, there are some very good reasons that this has not been done until recently. So dark matter-only simulations are quote-unquote easy, at least into comparison to trying to deal with baryons, because the only physics that you need is gravity, right, to deal with dark matter. If you want to be able to simulate a reasonable set of galaxies along with that dark matter, you need a tremendous amount of baryonic physics to also go into your simulation. First and foremost, you need to account for hydrodynamics to work with the gas from which stars and therefore galaxies will form. You need to know how stars form from that gas, how those stars evolve, how they feed back into their environments through supernovae and stellar winds, how supermassive black holes form, how they accrete, and how they feed back into their environment. And it would also be good to have some radiative transfer and radiative cooling as well. So as you might imagine, this is pretty complicated. And not only is it complicated, it is also expensive computationally, much more than just gravity. Now you may have noticed that these next 4 bullet points, star formation, evolution, supernovae, black holes, all of these are full-fledged subfields of astronomy in their own right. So there are people who work on star formation simulations and stellar evolution simulations and supernovae simulations. And moreover, these processes operate on scales that are just unattainable if you want to be able to simulate the structure of a whole galaxy. You can't go from galaxy sizes to star formation sizes or black hole event horizon sizes. So the way that these work in the galaxy formation community is that we talk to the people who work on these things and get subgrid models for how they will affect the galactic evolution. And of course, all of these have some level of uncertainty associated with them because they are, in fact, active areas of research. Radiative transfer is, at this point, wishful thinking because it is extremely expensive and difficult to do in a robust and consistent way. And so, by and large, even zoom-in simulations of galaxies don't account for radiative transfer at the time. So this is treated in a similar way when it's going to affect the way that the galaxy evolves. For example, by radiative cooling, there are subgrid prescriptions for this too. And then you can go back after the simulation is finished and do some post-processing radiative transfer if you want to get some pictures, for example, of what it might look like. An additional difficulty with doing cosmological simulations is that the computational costs can be prohibitive because there's enormous dynamic range that you have to cover. So if we think about how big a volume has to be considered cosmological, you're going to want a minimum size of tens of megaparsecs. And if you want to resolve the structures of galaxies, you're going to have to go down to sub-kiloparsec scales. So that means that you're going to need at least 4 orders of magnitude of dynamic range in the simulation, and that's a lot to ask. But all of these problems, things like computational expense, numerical techniques, understanding the physics, all of these things get better and better with time. Computers get more powerful, we develop better numerical techniques, we start understanding the physics better and better, and in recent years, trying to do baryonic cosmological simulations has become an approachable problem. So here at the CfA, we have recently run a cosmological simulation called Illustris, which I'll show you in just a slide or so, which was run on some of the most powerful supercomputers in the world, including SuperMOOC in Germany and Curie in France. So our simulation is called Illustris, and it's a periodic cube of about 100 megaparsecs on a side. And within this volume, there are tens of billions of resolution elements, which includes everything from dark matter particles to gas cells to star particles to black hole particles, which are evolved using all the physics that I talked about earlier. In total, the simulation took 19 million CPU hours to run from very high redshift down to the present day. And because the simulation has such high volume and such large numbers of galaxies, it can actually reproduce some very important statistical properties of galaxy populations. So this picture down here is actually 2 separate pictures, one of which is the Hubble Ultra Deep Field that I showed you earlier, and one of which is an approximation of the Hubble Ultra Deep Field using mock observation techniques and data from the simulation. And at least by eye, the 2 sides of this picture look pretty similar, although in detail there are some differences because we don't completely understand the physics, and if we did, we'd be out of a job. So the real key way to tell the difference between these 2 panels is if you look at this guy over here, that's actually a star that's in the way, and you can see diffraction spikes on the star. So that's an observational artifact that tells you that this is actually the UDF, and this is the Illustris mock ultra deep field. So this is great. So now we can actually make statistical comparisons. All right, so this will give you an idea of what the simulation looks like and the dynamic range involved. So let me stop here for a second. So it's going to flash through a couple of different quantities as we zoom in. We're starting at the largest scale in the simulation. You can see how big the box is because there's some repeated filaments on either side. It's a periodic box, so that means that what goes out one side comes in the other. So this effectively shows you how big the box is, 100 megaparsecs. And we're starting out with the dark matter density, which is just like what I showed you earlier with the Millennium simulation. All right. So we're starting out at this biggest size, zooming in. We've got the dark matter filaments and voids that we saw earlier, but on top of that is also baryons. So now we're looking at the temperature of the gas. Red means hot. Yellow is slightly cooler, so this is where you have cold gas forming stars. So those are where the galaxies are. Now we're looking at the gas metallicity, and you can see some high metallicity outflows, for example. And then in addition to dark matter and gas, there are also stars in the simulation. And what we're looking at now is what we might observe in the stellar light being given off by those star particles. So we're zooming in now to the tens of kiloparsec level and seeing a nice spiral galaxy that exists in the simulation at redshift 0. Now going back out, we're looking at the gas density. So you see a big disk of cold gas around that spiral galaxy. And each of these little points here is a point of dense gas, which is essentially where stars are being formed in galaxies. So this gives you an idea of the number of galaxies that are in the box. Keep in mind that this is just a slice through the middle of it. And now we're going into the velocity structure. So you can see the effect of feedback on the velocity structure of the gas. And now shifting back out into dark matter, which comprises the backbone of the structure. So now we have, rather than some preconceived initial conditions, we have sort of natural initial conditions on which galaxy formation can happen. So here's a smaller piece of the box, and there's two quantities evolving in time here. This is stellar light. So this is kind of what you would see if you were to look at it with a telescope. And here's the underlying gas structure. So this is gas density. And you can see here a filament in the gas, which is tracing a filament in the dark matter that's underlying it. You can see galaxies which are star forming, which possess a lot of gas. And you can see galaxies interacting with each other here. So you'll see in a bit galaxies merging with each other, kind of like what happened in the earlier simulation, but in a much more sort of chaotic manner. You'll see every once in a while also some little puffs of gas there. That's from black hole feedback. And you'll see lots and lots and lots of little mergers here. So now we're starting to really get into it. So again, this is what we see when we just look through telescopes, and this is all the chaos underlying it. There's another black hole, and we see the coalescence of many, many galaxies coming to form one giant elliptical galaxy at the end of the day. There's a big star-forming spiral galaxy coming by. So again, a similar idea to what I showed you earlier, but happening in a more sort of chaotic and quote-unquote natural way. So what is the science that we can do with this? So I'm going to tell you a little bit about the specific science topic that I have been working on for the past year or so, which is a particular population of galaxies called compact ellipticals. I showed you one right at the beginning. And let me give you a little bit of observational background before I dive into the simulation results. So this is observational data here in front of us. Each of these panels is a distribution of sizes, measured sizes of observed galaxies. The galaxies have been separated into star-forming galaxies in blue and quiescent galaxies in red, and each panel is a bin in stellar mass going up and down, and in redshift going left and right. So if we look around here, around redshift 2, around 10 to the 11 solar masses, we see that there is a big difference in the typical size of a quiescent galaxy and a star-forming galaxy. And these galaxies are very, very dense. When we look at images of them, so these are HST composites, this is real data, you can see why these galaxies are sometimes referred to as red nuggets. And moreover, if you look at where the peak of the histogram is, in the red histogram, and trace it forward to low redshift, you see a very strong evolution in the typical size of a quiescent galaxy with redshift. And in fact, when these sizes were first measured, when this population was first discovered, people didn't actually believe it. They said, you must have messed up the observations somehow. There's no way that this galaxy is that dense. You know, how do you even do that? But the observers really drilled down on it, and the initial observations have been borne out. They really are this small. And so these observations have prompted a lot of interest in both the observational and theoretical communities. And there are a couple of questions that have been posed about these galaxies. Like, how do you even form something that dense? And what happens to them at low redshift? Why are these galaxies, which were so common at high redshift, so much less common at low redshift? I've worked on both of these questions in the context of Illustris, but I'm going to be telling you mostly about this last question, what happens to these galaxies at low redshift? So the nice thing about the simulation is that you can just go straight to redshift 2 and ask, are there galaxies in the simulation that are similar to the ones that we observe? So here is a scatter plot of stellar mass on the x-axis against stellar half-mass radius on the y-axis of all of the galaxies in the simulation above a few times 10 to the 10 solar masses at redshift 2. So the half-mass radius here is the radius of the sphere that encloses half of the stellar mass that is bound to that galaxy. So it's a measurement of the size. And I made a cut in this sigma 1.5, which is sort of a surface density cut, and picked a certain stellar mass range here. And I got a population of compact galaxies. Now, just to give you an idea of what these guys look like, here are a bunch of mock images of galaxies from the simulation at redshift 2, all of which have a few times 10 to the 11 solar masses in stars. These galaxies on the left are some nice, big, beautiful spiral galaxies, which do not fit my compact criteria. And these galaxies on the right have the same amount of total stellar mass as the galaxies on the left, but pack all of it into a much smaller, denser region of space. So these are the guys that I'm talking about. These are the compact galaxies that fall into my selection criteria. We can also ask, what might these galaxies look like if we were to observe them? So these are mock observations, where essentially what we've done is we've taken the light given off by the star particles in the simulation, redshifted the SED to a redshift of 2, integrated over the HST bands, binned it into pixels, applied the point spread function for the HST camera that was used, and put in a little bit of background noise, and voila, you get these mock observations on the left. Now if I bring back up the 6 examples that I showed you earlier of real observations of compact ellipticals, you can see that, at least by eye, these simulated galaxies look like pretty decent analogs to the observed galaxies. So we have some confidence that if we can figure out how galaxies like this form in the simulation, it might tell us something about how galaxies like this form in the real universe. So again, the nice thing about simulations is that you can pick a galaxy out at one moment in time and just follow it around. So to address the question of what happens to these guys at low redshift, I took all these galaxies that I picked at redshift 2 and just followed them forward to redshift 0. And this is where they end up, on the same size mass plane. So you can see that their stellar masses have dispersed enormously all over the massive galaxy population here. And this actually runs kind of counter to the way that people usually talk about galaxy formation. We can further look at what these galaxies look like, what their descendants look like, and where the compact progenitor ended up within that stellar distribution. So this is the same size mass plane at redshift 0 that I showed you in the last slide. And now I've replaced all of the compact symbols here, descendant symbols, with a little postage stamp image of what the descendant looks like. These are kind of funny pictures because there are two axes in the color bar. Light to dark indicates fraction, which means the fraction of the stars along the line of sight that were present in the original compact progenitor. So this tells us where those original stars ended up in their descendant. So by definition, if I go down here to the low mass end, these galaxies haven't gained much stellar mass. It's basically all the same stars, so they look pink. And up here at the high mass end, they've gained an awful lot of stars, and so by definition, they look mostly blue. Now, if we zoom in on these images here, we can see a few interesting features of the descendants. A lot of them, especially around here, you can see a color gradient from the inside to the outside, where the middle is mostly red and the outside is mostly blue, which tells us that the core of the descendant is dominated by stars from that compact progenitor. Whereas in some of these guys up here, you don't see any obvious signature of where the compact galaxy went. In some of these, if you have very good eyesight, you can see kind of a band of green going across it. Progenitor masses. You see again this kind of color gradient effect going on here, some fun morphologies. This guy is clearly in the middle of tearing something apart. And if we go down even further, we see these galaxies which are mostly red, essentially the same as they were at redshift 2. All right, so how did they get that way? Well, we'll look at a couple case studies to find out how these different kind of descendants came to be. If we go to the high mass end, let's pick out this guy here, one of the ones that's mostly blue with a band of green going across it. This is the evolution in stellar mass as a function of time. Here's redshift 2. Here's the present day. There are two lines here. One is for the evolution in stellar mass of the compact galaxy, and then you see this big jump here, around 9 gigayears. So that shows the point in time when this galaxy was eaten by something, and the thing that ate it is indicated with this dashed line here. So if I put up pictures of what it looked like at that time, so each of these pictures corresponds to one of these big dots here, we see that it was more or less minding its own business here. It grew a little disk, which is fun. You can see that it's starting to fall into something because the outsides are all blue. And at this point, it gets totally ripped up and destroyed by the thing that it falls into, scattered around, and you just see this little remnant of green at the end of the day. And we can also look at the evolution in the half-mass radius as a function of time. Here, it's not changing much, although you can see a little tiny difference here. So red now is the half-mass radius of only the original compact stars. So the same stars that are painted in red here. So you can see it's not changing much. It jumps up when it gets destroyed and has more or less lost its identity thereafter. Moving a little bit further down in stellar mass, we see one of these guys that has a red core and a blue outside. Now the stellar mass evolution is a little bit more gradual. We see here these vertical lines indicate that the galaxy had a merger with another one, and this is the mass ratio. So these lines tell us that at 2 points in this galaxy's history, it had a merger with a galaxy that was about 75% of its mass. If we look at the pictures here again, we see this guy disrupting this other galaxy, hanging out, disrupting another galaxy, and it is clear that during this time, basically the opposite happened here as what happened in the previous slide. This galaxy disrupted some other galaxies and accreted their stellar mass onto its outsides. And again, when we look at the stellar half-mass radius, the radius of just the same stars that were here doesn't change very much, whereas the overall half-mass radius changes a whole bunch. If we look at this guy, which was mostly green, we see that it was mostly minding its own business for almost the entirety of its lifetime, and then had a major one-to-one merger shortly before redshift 0. Here's what that looks like, minding its own business, merger, in spiral, and this is why it's so green. And again, there's a jump when the core kind of gets disrupted during that merger. And finally, this guy down here is mostly red, and as you might be able to guess, it's not very exciting, not very exciting, not very exciting. It is actually interesting that it's this unexciting, believe it or not. But it's not very interesting to look at, that's for sure. So I've shown you now the variety of things that can happen to these galaxies, but how do we sort of quantify this a little bit more? Well, one way that we can do it is by looking at the cumulative mass profiles of these galaxies. So here now I'm showing basically the enclosed mass, the enclosed stellar mass at a given radius, where the black line is all the stars and the red line is just the stars from the compact progenitor. So this guy down here, the two lines are essentially the same. This guy down up here, the black line is well above the red line because the compact progenitor is just a small fraction of its descendant's mass. Here, it has a sizable and more or less constant fraction of the stellar mass at all radii, and here you can see that the compact galaxy dominates the core, but that then there's a bunch of other stellar mass out at larger radii. So we can classify all of these descendants according to their cumulative stellar mass profiles. If we pick two radii, signifying the core in here and the outer parts out here, we can classify any galaxy which has if you compare the values of the red and black lines, if these fractions are small, very small at both radii, we can call this consumed. If they're very high at both radii, we can call it more or less undisturbed. If they're middling at both radii, we can say that it's mixed. And if it's very high at this radius and low at this radius, we say that that's a core. And in so doing, we can classify all of the descendants. And when we do so, we find, somewhat unsurprisingly, that the most massive descendants are mostly the ones that have eaten the compact galaxy at some point in time. The lowest mass descendants are the ones that have just been sitting around, and the most common type of descendant is this core type galaxy. So here we have been able to reach into this cosmological volume, pluck out these galaxies and ask how they got the way they did and what happened to them. And moreover, we can do so with sort of a statistical selection of galaxies that makes it somewhat comparable to observations. So I hope I've convinced you that cosmological simulations like this can be a very powerful tool for trying to figure out how galaxies form and evolve and for making meaningful comparisons with observations. So where do we go from here? What can we do? Well, we've really only scratched the surface of the abilities of these simulations. These are really just the first generation of baryonic cosmological simulations. So as time goes on, we're going to be able to get larger volumes and higher resolution. So we'll be able to improve the statistics even more and say something about the structures, the detailed structures of the galaxies in the simulation. We'll be able to improve the physical models that go into the simulation. Just with this one, we've already learned about parts of the physics that we don't understand, that aren't quite acting the way that they should. And as we get better statistics, and as the observers do better and better, we'll be able to converge and start speaking more of the same language and make better observational comparisons. All right, so I hope I've convinced you that this is a very cool, sort of emergent area to be working in, and thank you for your attention. Are you talking about this?
No, the actual simulation.
This one?
Yeah. So that shows all those filaments?
This was actually gas density, but it is tracing the filaments.
Okay.
Yes, yes.
So I know that this is like a pretty new, I guess, suggestion in theory that like gas could be falling, like falling gas could like move from one galaxy to another.
Well, so you can, so gas can fall into galaxies and get kind of processed by star formation and flung back out by feedback, at which point it could then plausibly accrete onto another galaxy later on. So there could be some contamination, yeah. Is that what you're asking?
Kind of. Maybe the question isn't fully formed in my head. This being like a new mechanism behind like how dwarf galaxies form and how they form stars. And I know that
Oh,
this
yeah.
is something that E.J. Hunter has been working
Okay.
on many years ago.
So dwarf galaxies, well, so first of all, dwarf galaxies aren't quite really resolved in this simulation. But yeah, dwarf galaxies are kind of a different breed from the massive galaxies that I've been talking about, in the sense that they're generally like satellites that are pretty close to another galaxy. So there, I can totally see contamination happening, yeah. With a lot of help from your friends.
Like which language and just, I don't know,
Yeah, so I mean, you're going to want something like C, for example, or C++, because you want these to run as efficiently as possible, right? You don't want to do like Java or something. So you're going to want to be able to work as closely to the computer hardware as possible. So that's the kind of language that you're going to want to use. But these simulations like this is a massive, massive undertaking and took a team of like 10 people to do this, of which I was not a part, by the way. I'm just piggybacking off their hard work.
So it wasn't clear to me, but it seemed like nothing ends up, or more or less nothing ends up being compact by the time you get to zero.
Yeah, it was like 10% of them. Yeah.
So, I mean, the number densities of compact galaxies are more or less constant from 1 to 0. It's, or at least a lot of observations are suggesting.
Yeah,
that
it seems to me that that's something that people are kind of fighting about, but yes, some of the observations
Are
suggest
your
that.
simulations consistent with that, or are they?
I haven't made direct comparisons between the number densities because it gets a little hairy trying to make direct comparisons between simulation quantities and observed quantities. But it does seem to me like the ways that you make compact galaxies physically kind of require the conditions of the high redshift universe. And so it's hard for me to imagine that as you stop making them and they start leaving the compact regime for some reason, that the number density doesn't decrease, unless there is some other like replenishing mechanism for making them. So that's what I think based on the simulation.
Yeah, so would you, for example, like tidal stripping as a mechanism, would
Yeah.
your simulations resolve that mechanism, or are the resolution?
So there is one, for example, let's see, where is it? So this one, right at the bottom here, that's actually an example of that. So this one actually lost mass between redshift 2 and redshift 0 because it like dove right through a dark matter halo and got like really, really stripped along the way and is just coming out the other side at redshift 0. So it probably depends on the mass regime that you're asking about, to be honest. And I think that's another reason that I'm hesitant to compare number densities with observations, because I can really only talk about 10 to the 11. I can't talk about 10 to the 10.
Yeah.
Yeah.
So in this part, sorry,
Yeah.
last question. Your stellar mass size relation looks flat. Is that just a selection effect of the resolution?
So part of it is because this includes both star forming and quiescent galaxies.
I see.
So this is sort of the quiescent galaxy size mass relation.
Okay, so that's consistent with the rest of the population.
It's not, I mean, it's not perfect. Definitely the size mass relation in Illustris is not ideal, especially at lower masses. But up here at these masses, it's decent.
Okay, thanks.
Mm-hmm.
How much will your result differ when you change the initial condition for?
So the initial conditions shouldn't make too much of a difference, because if you remake the initial conditions, you'll do it in such a way that the statistical properties are preserved. And since the volume is so large, you should recover the same general results, even if you reinitialize those conditions.
So when I looked at that earlier plot, the one which had the stars filling factor wasn't that big of places where interesting baryonic physics was going on.
Sure. Well, it depends on what you mean by interesting, but yes.
Right, well, stuff that you couldn't do analytically.
Sure.
And so I'm wondering whether that's, there's some optimization to be done there. Or actually, really my question is whether, to what extent does the baryonic physics participate in long-range interactions where you can't reduce it to a subgrid model?
You mean long-range interactions between different galaxies?
Yeah, right, exactly.
So those would be covered, those are mostly dominated by gravity, long range, right? So yeah, that's not going to matter too much. And in fact, you could infer that from a dark matter only simulation, right?
Right. And so
If you appropriately populated the dark matter halos.
And it's just my suspicion looking at that, that having learned from this, you could go back and do a simulation where the long-range stuff is just dark matter, and you put back in the baryonic in more recipes that you don't have.
Yeah, so this is something that I am thinking of doing actually, is taking little pieces of Illustris and doing higher resolution simulations of those pieces and trying to change the physics a little bit to see how it changes. But there, it's nice that it's embedded in a larger simulation, right, where you can have reasonable initial conditions and boundaries. But definitely that's something, the trouble is that rerunning the whole simulation just for tweaking the physics a little bit is 8 months of supercomputer time.
If you only rerun the dark matter.
If you only rerun the dark matter,
And because you understand the baryonic stuff is now local, and so you can put it in afterwards.
so you want to reinitialize the dark matter and then populate the dark matter halos according to some like stellar mass halo mass relation kind of
That
thing.
you've shown through this that you can reproduce.
Yeah, that doesn't sound as fun.
So don't
Yeah.
you do the dark matter halo simulation first and then do the hydro afterwards?
Yes, so there's,
You're already doing what you suggested.
Yeah, okay. And I guess what I was suggesting was that you maybe don't need the full dynamic range for the hydro if it's all local.
But they have adaptive mesh, right?
Yeah.
yes, yeah, it's an adaptive mesh. It's not, 100 parsec resolution throughout the entire volume. Yeah, yeah. But yes, there are actually 6 simulations within the suite, 3 of which are dark matter only.
So since there's such a wide dispersion in the speakers, did anything come out that would be a good way to identify these galaxies observationally?
That's a good question. So one way I think to do it would be looking at the density of the core, because when you start out at redshift 0, by definition, these have the densest cores. And when you follow them forward, they get a little less dense, but they still remain some of the densest cores in the simulation. So that could definitely be one way. Another way would be to look at the ages of the stars, because these are all stars from redshift 2, right? So yeah, core density, I think, and age would be 2 ways.
Well, it seems like we have no further questions. If you have any future questions, you can easily ask Sarah. Her room is A207. Yeah.
Thanks, everybody.